Okay, so we are going to start a mock interview for our student Pramod. So Pramod, this interview is for ISRO exam, right?
Yes, sir.
Okay. So give us a brief introduction first.
My name is Pramod. I did my bachelor's from BTU Belgaum, Karnataka. After that, I did my master's from IIT Hyderabad. I've been working as an analog circuit design engineer, like for past 6 years. Along with that, I have in my master's actually I have my research projects has ended up in 3 conference paper and 1 in transaction of circuits and system. Presently, I am also I am also an active reviewer of the same transaction.
Okay, so you have very good academic profile, right?
Yes, sir.
So, do you have any plan of pursuing PhD in your research area? Circuit design?
Sir, as of presently, I don't have any plan, but in future, provided an opportunity and work if my work demands so, I'll actually definitely go ahead and do it, sir.
Okay. So, what was the reason behind going to this analog circuit design domain?
After my B.Tech, one of my seniors who was actually return gate, we had it was actually my senior's opinion actually that attracted me to move towards the microelectronics and VLSI. When he came and gave us a talk at my BE University, and the special interest for analog evolved when actually I was pursuing my master's.
Okay, so generally we listen 2 branches. One is microelectronics and another one is VLSI.
Yes,
can you tell us the difference? What is the difference?
The microelectronics specially deals with the devices. The modeling of the devices and the fabrication of the devices is what it actually mainly deals with the physics of the devices, wherein actually we try to model a different kind of devices, whether it's a normal Cmos process or a BJT by Cmos. The other part is the VLSI is nothing but an integration of these such devices to form a large scale integrated circuits based on the scale of integration.
Okay, now you tell me, have you heard about OTA?
Yes, sir. Operational Transconductance Amplifier.
Okay,
Yes, sir.
so tell us something about OTA.
Sir, Operational Transconductance Amplifier is one that actually has a very high output impedance and a very high input impedance as well. The OTA actually given an input V in, a small signal V in at the input side, it generates the GM times of the output value, where GM is GM times of the input voltage. The current out, the GM is the transconductance of that amplifier, sir.
So how is it different from op-amp?
Op-amp is actually has a low output impedance, sir, whereas OTA has a very large output impedance. And the gain of the op-amp is generally in terms of voltage. The output is voltage and the input is generally a voltage, after which we can actually whereas here the gain is actually in terms of that conductance. The output is current and the input is voltage.
Okay, so what is this unit of conductance?
Is MOH, sir. MOHO.
Okay, so conductance, conductivity, same thing or different thing?
Sir, just conductivity and conductance. Okay. Those are different things, sir. As resistance and resistivity are different, the conductivity is like exactly.
What is the difference? Can you explain us?
Yeah, okay. Conductance says how easily a medium is allowing the flow of electrons or the charge carriers. Conductivity is a parameter it is defined per unit length kind of stuff, sir. In terms of sheet resist, okay, Just a minute, sir. I'll just get you the exact thing. So 1 over resistivity is actually the conductivity. So if you look at that way, it's moles per meter is what it comes down, sir. So it's a measure of resistance per unit length kind of stuff. Measure of conductance per unit length.
Okay. Okay, now tell me, what is your plan for your future? What do you have think about career in life?
Sir, as of now, my thought process is to get into a certain good R&D organization which can give me a good exposure into the research domain, like not into the research project, challenging research projects, where I can accomplish and prove myself is what my current aim. Coming into the future, I want to grow more into the technical domain and try to contribute in the same area as much as possible.
So there are various all India level organizations, as you said. Why ISRO?
ISRO is an accomplished organization which has proven its track record in past decade or so with its capability, and it has made its name across the globe as well, as we know. The thing that actually focuses me to actually end up in ISRO is that it's majorly related to it has a large number of verticals where actually it has in circuit design itself, if you can look at it, it actually works on each and every part of it for the satellites as well as ground stations. And it majorly focuses on a satellite, which is a core area for electronics and communications. That's
Okay.
why it's a part of it.
Do you know Chandrayaan 3?
Chandrayaan 3, they are planning for launch, sir.
Okay.
Yes.
So how is it different from Chandrayaan 2?
Chandrayaan 2 actually has a orbiter and a rover, and the orbiter, lander, and a rover. Chandrayaan 3, yeah, I feel so. It is the same thing. I need to like get into much of it. I don't exactly.
Okay. And what are your favorite subjects which you have studied in your B.Tech?
Sir, my favorite subjects in my B.Tech are analog circuits, analog integrated circuits, digital circuits.
Okay.
After that, control systems, communication, and signals, sir.
Okay. So tell me, what is a full adder?
Full adder. Full adder is a block that actually takes it is a bitwise adder. It is a 3-bit kind of thing where it actually adds 2 bits which are coming, it's just if I it actually has a 3 inputs which are A, B, and the carry inputs, and it gives away the output as the sum as well as carry at the output.
Can you draw the block diagram?
Yes, sir. I'll just try it. I don't know whether is it visible, sir. Is it visible, sir?
Yeah. What is parallel adder?
Parallel adder is one that actually takes multiple inputs at the same time and actually gives away the sum and output at like.
Okay. So parallel adder is a combination circuit or sequential circuit?
Parallel adder is a combinational circuit, sir. In that.
And what is combinational circuit?
Combinational circuit is one that actually the output at the present will be dependent on the the output. The present output will be only dependent on the present inputs, not on the the previous inputs or the states of the system.
Okay. Do you know sequential circuits can be classified into 2 categories?
Asynchronous and synchronous.
Something.
Okay. Yes, sir. Mealy and Moore.
Yeah. What is the difference?
Melee circuit, actually the output is defined, but the output is dependent on the present as well as the states of the system, whereas Moore, actually the output is only defined by the states of the system itself. It only
More on
depends
the
on the
input.
state.
Output also depend upon the input in More, right?
Yes, it only depends on the states of the, like, the next state will be dependent on the previous.
Okay. Okay. Tell me any one application of serial input, serial output, shift register.
Sir, serial input and serial output. Okay. It can be used as a delay element, sir.
Okay. How do we get delay?
Sir, whenever a signal is, and a resistor is one that stores the signal as and when data comes in, it captures it and it actually delivers at the output by the delay. Like if there are 4 resistor elements, 4 flip-flops in that system, then it will actually take a 4 clock cycle to get it out. Like, so
Okay.
there will be a 4 clock delay, 4 clock cycle delay.
Okay. Okay. So one digital circuit is your favorite subject, right?
Yes, sir.
And can you tell me what are flags in 8085?
Sir, actually, I can only remember the basic set of things. That is carry, auxiliary carry, sign, 0, and
so what does this flag represent actually? What is the flag made up of?
yeah, okay. The flags are actually stating the status of the operation, sir. What is a like current status of an operation, whether it's an addition or a subtraction or. Sir, sorry, sir, I am unable
We
to
have
hear
one
your
flag.
voice.
We have one flag. So what is that flag actually? How do we make that?
Sir, I am unable to hear you properly. Can you repeat one more time, sir?
How is this flag made?
Okay, sir. In case of a carry flag or a zero flag, whenever the output of a certain operation
No, no,
goes
no.
to, yeah,
Flag
it is
hota
made up
kya
of.
hai actually? What is this flag actually?
It's a resistor, sir, having bits pertaining to the output of a result. It states what kind of result is there, which can be make out of it.
One flag means one register.
No, sir, it's a bit in a resistor.
Okay. So one flag means what?
Flag, sir, sorry, sir, I am unable to get your.
One flip flop cannot
Yes,
be.
sir. Yeah, yes, sir. Yes, sir. Yes, sir. One, it's a resistor. Yeah. Yes.
Okay. Okay, Kailash sir, you may continue, sir.
Hello, Pramod, how are
Hi,
you?
sir. Fine, sir. How about you, sir?
I'm fine, I'm fine. Okay. So please elaborate about your work profile. What was your work profile?
Sir, my work profile, actually, I have worked in 3 different companies as of now.
No, what was
After
your latest work profile?
my latest work profile is an staff analog design engineer in a startup, sir.
So what is your role there?
My role presently is to design a reference circuit that is a band gap reference along with a current reference blocks for which is
What do you
actually
understand
biased.
by band gap reference?
Okay, sir. Band gap reference is one that actually eliminates the process voltage and temperature variations so that it gives out a clean reference to the other blocks.
So earlier to this, so now you are working on the band gap reference. Earlier to
Yes.
this, what we were using as a reference?
Earlier to this, sorry, sir, I didn't get it.
So this might have replaced certain technology, no? Okay.
Okay.
Is there any drawback of this band gap reference?
Sir, it cannot drive heavy loads. Only it can provide like it can only drive some capacitance. Like it will unable to drive a load.
Okay, so can you tell me, what is the main constraint being an analog designer? What is your main constraint?
Constraints. Okay. Sir,
See, you consider it as like you are into analog designing, right?
yes, sir. Yes, sir.
I'm not saying that you might have that much exposure at this level, but if I am into designing of something, there are certain constraints
Okay, sir.
that
Okay, sir.
okay, this should be good, this should be bad, this should be worse, this should be best. Okay, so do you think
Okay, sir.
there are certain constraints being an analog designer?
Yes, sir. There are constraints on the amount of quiescent current we need to burn, which decides the overall performance of a system. The speed of a system is decided by it, because the I naught quiescent current which we burn decides the transconductance of an amplifier, which actually decides the unity gain bandwidth, that is GM by CL of a system.
What do you understand by this term unity gain bandwidth? Explain this.
Yes, sir. Unity gain bandwidth is a bandwidth where the gain of the system or a amplifier is greater than 1, below which.
Repeat it.
The unity gain bandwidth of a system or amplifier is a range of frequencies within which the gain of a system is greater than 1, sir, and above which the gain of the system drops below 1. And it actually acts as an attenuator beyond which.
What is the significance of defining this unity gain bandwidth with reference to any amplifier?
Sir, it says that it has a negative feedback capability below which it actually provides. If you keep a feedback loop and then the amplifier or a system tries to correct it, so it says that it has a capability to correct it.
I'm not saying in reference to feedback. See, whenever you purchase something from the market, okay, there are certain specifications.
Okay, sir. Okay,
so this unity gain bandwidth is one of the parameter of specification, right? So what information, if someone says you that the unity gain bandwidth of certain amplifier is 20 megahertz, what is the meaning of this? What you can conclude from this?
It says it is a fastness of the system, any signal that is actually varying at 20 kilohertz, it can actually tries to rectify it, kind of stuff. The fastness.
Okay, any other thing? Can we say that it also gives us the information that this is the maximum frequency up to which it can fulfill our objective of being amplifications?
Yes, sir. Yes, sir.
Do you think that above this frequency you can use that amplifier as an amplifier?
No, sir. We cannot, sir.
Then why are you surrounding all the things? You come to the basic point directly, na? Is the name is specifying? See, there are certain meaning of specifying. If I say power dissipation, what is the meaning of power dissipation? Don't you think that the power dissipation is the one of the main constraint as an analog designer? Don't you think this one?
Yes, sir. Yes, sir. Yes, sir.
Okay, so have you listened about Cmos?
Yes, sir.
So do you think that in Cmos there is power dissipation?
Yes, sir. In case of analog circuit, whenever we design, there is a power dissipation with respect to Cmos. But
can you tell me what are the different sources of power dissipation in Cmos? Is there only one source, or is there multiple source, or see, when a circuit operates,
yes, sir,
so it operates under different situations.
Yes, sir.
Right? You understand?
Yes,
okay.
Yes,
it appears to us that everything is happening instantaneously, but it doesn't happen like that. Fine. It takes a time and responding time, rise time, call time, which is in nanosecond and microsecond. Obviously not observable to a human, right?
Yes, sir.
So there is a term power dissipation. If we talk about CMOS, can you suggest me what are the different sources of power dissipation which contribute into the dissipation of power, which you might have studied or observed during your work?
Okay, sir. One thing is that any system needed to be operated in a equilibrium, in equilibrium state, where we actually it dissipates a quiescent power once we have actually set its operating point.
That is a static power. Okay, that is not in the CMOS case. Okay, CMOS is the biggest advantage that it don't have any static power, right? It have but negligible.
Yes, okay, sir. In the sense, in case of digital, it's actually the switching, switching power dissipation is what is there, sir. That is dynamic power dissipation, which is directly proportional to the frequency of operation.
Okay, what is the dynamic power dissipation? Can you tell me the expression?
Yes, sir. Is F into C into VDD square, and alpha multiplied by alpha. Alpha is like a switching factor, like how much switching is happening. It actually says.
Okay, so this is the dynamic power dissipation. Do you think that this depend upon the size of transistor?
Yes, sir.
How?
The size of the transistor, actually, if you are actually trying to if the only case where it actually defines is that if you have two sets.
You told me some factor alpha, yeah, switching for factor, yeah, either I take a frequency f, right?
Yes, yes, sir.
One you told VDD, one you told CL. So tell me,
Yes,
which
sir.
factor is depending upon the dimension? Is there any factor which depend
yes.
upon the dimension?
Sir, in case of digital, sir, when we actually model the CL, the load capacitance, it actually includes the CDB capacitance, the drain to like bulk capacitance of the PMOS as well as NMOS, and the CGD capacitance, the capacitance that are connected to the output node, the parasitic capacitance, that will also come into picture. Even if the CL is very much greater than the inherent parasitic capacitance, then we can negate it and say that it's independent of itself.
What are the other sources? One source you told me, the dynamic power dissipation. Any other sources? Do you think any other sources are there also?
Any other sources? That there is a crowbar current that flows out from the supply to the ground, sir, when actually switching is happening.
Have you listened about certain points short circuit powers?
Yes, sir. Yes,
practically,
sir.
is it possible that for a few seconds, due to the finite rise time and fall time, both NMOS and PMOS get on simultaneously?
Yes, sir. Exactly, sir.
So will there be any power dissipation or not?
Yes, sir. Yes, sir. That's the crowbar current that flows when both the transistors are on, sir.
Okay. Have you listened the term sub-threshold conductions?
Yes, sir. Sub-threshold conduction. Yes, sir.
So don't you think they also will contribute to the power dissipation?
Exactly, sir. Exactly. Yes, sir.
See, there are so many constraints. Okay, because you have worked in the power management unit, so power dissipation is the one of the concepts they can focus more into, right?
Yes, sir.
So what are the various sources of power dissipation? I will share one PDF with you right now after this interview. Just go through that, okay? Sometimes they can ask even to drive this formula which you told me, the dynamic power dissipation. They can go into this direction also. Is it clear?
To derive it, sir?
Yeah, they can ask to drive it. Okay, obviously, first of all, they will say you to design the Cmos inverter. Obviously, you will design the Cmos inverter, right?
Yes, sir. Yes, sir.
So then they will ask, can you drive this relation? Everyone can tell this relation. Okay, this is the power dissipation. But sometimes they also ask to drive because they have enough time. Okay.
Okay,
sir. Okay, have you listened the term DAC?
DAC, sir. Yes, sir. Digital to analog converter. Yes, sir.
Okay, can you draw a circuit of 4-bit switch capacitor DAC? Have you listened the term switched capacitor DAC?
Switch capacitor DAC. Sir, I haven't designed so, but I have listened, sir.
Where you listened? When you listened it?
Sir, actually, capacitive DAC is what I have listened. So switch capacitor. Sorry, sir. Switch capacitor. So sorry, sir. Capacitive DAC is what I have
Okay, you have studied a D2A converter, I guess some weighted R2 or something.
Yes.
You have studied. Can we replace those resistors with capacitor or not? Tell me.
Yes, sir. Yes, sir. We can replace, sir.
So don't you think under that condition it is the switch capacitor DAC?
Okay, sir. Sorry, sir. Capacitive DAC. Okay, sir. Sorry. Yeah. Okay. Okay, sir. Sorry. Yes, sir. Yes, exactly.
Okay. Do one thing. Take a N-type semiconductors.
Okay, sir.
Okay.
Yes, sir.
And it is uniformly doped.
Yes, sir.
Right?
Yes, sir.
And nothing connected externally.
Okay, sir.
Can you draw its E versus X diagram?
Okay, sir.
Venn diagram.
Yes, sir.
What is this dotted line you have drawn in between?
That is intrinsic semiconductor Fermi level, sir.
Okay.
Fermi level of intrinsic.
Now, if there is non-uniform doping, then?
Okay, sir. Can I assume left side to be like heavily doped?
You can assume, no issue.
Okay, sir. Is it like a linearly variation or how is it, sir? Like
linearly. Linearly variation you can consider.
Okay, sir. Could be kind of this, sir.
Which one? I'm not able to get.
Okay, sir. Just a minute.
Maybe your coffee.
Okay, sir. Just a minute.
Okay, what is this? EF is having certain slope or it is a constant line?
It's a constant line, sir.
Okay. So can you tell me why? What is the reason behind it? Why you have banned this EC and EV? Can you explain this?
Okay, sir. Sir, the Fermi level is actually states the equilibrium state, sir. In equilibrium, the Fermi level will be constant of a system. The EC and EV, the closeness of EC and EV with respect to EF is defined by the doping level, sir. So generally, as you go on increasing the doping, in the donor doping, the EC moves towards the EF, sir.
Okay, what information you can get from the slope of this conduction band energy level?
We can get the doping.
What is difference between these two? You have drawn two energy diagram. Okay, one
yes,
you have provided the constant height, right?
Yes, sir.
In other there is certain slope.
Yes, sir.
So if someone mention me these are the two
yes,
energy band diagram of certain specimen.
Yes, sir.
So can we comment on the some electric field present in the specimen or not from the band diagram?
Yes, sir. Yes, sir.
So in both of the cases, in under which condition there will be electric fields?
In the there is where there is a doping gradient, sir, where actually the slope is there. Slope.
Okay, why there will be electric field?
Because the concentration of electrons will be different at different edges, sir.
Mm-hmm.
So that's why.
So then.
Because this actually the different concentration leads to a development of potential difference. Different charge concentrations. Free
okay.
Charge.
Suppose you are having an.
Yes,
hello.
Sir. Yes, sir.
You are provided with some fan out.
Yes, sir.
Okay.
Yes, sir.
If I load the output with more than its rated fan out.
Yes, sir.
Will it be advisable or not?
No, sir. It's not advisable. First, the system will slow down. Secondly, the output of the system will not reach to a specific output value in a given within a given duration.
Any other effect? Will there be any effect on the speed of the operation?
Yes, sir. It will decrease the speed of operation, sir.
And will there any effect on the power dissipation?
In case of fan out, the maximum current will be defined by fan out, sir. In case of TTL, so it should not. It will not be able to drive extra current in that case.
So tell me, will its power dissipation affected? Power dissipation of each gate will be affected or not?
Yes. Yes, sir. In the sense, because the IE if I take an example of TTL, the output fan out, if I actually load with multiple set of transistors, each transistor will have its own fan-in current, which actually will determine the overall dissipation, sir. I do agree.
Are you sure about this?
Yes, sir.
Okay, you are also interested in signal system. There is something visible on your screen. Is it visible?
Yes, sir. Yes, sir. Yes, sir.
It is the Fourier series coefficient, complex exponential Fourier series coefficient versus some k, right?
Yes, sir. Yes, sir. Yes, sir.
You can draw it.
Yes, yes, sir. Just a minute. Okay, sir. I am drawing it.
Is it clear?
Yes, sir. Yes, sir.
Can you tell me, what will be the fundamental time period of the corresponding signal?
Fundamental time period. Okay. Sir, this is not a periodic signal, right, sir? Like,
see this, listen first carefully. This is the complex exponential Fourier series coefficient.
okay, sir.
Okay,
Okay,
this is
okay.
not a signal. This is
Okay,
the
okay,
complex exponential Fourier series coefficient of any periodic signal, right? Versus
okay, sir.
k. Is it clear?
Okay, sir. Okay, sir.
So can you comment on the fundamental time period of the signal whose Fourier series coefficient representation is this one?
Sir, Fourier series. So, here is k is actually like is 2 pi by t is what we get in Fourier series, sir. Like
That you need to decide what we got.
t is actually each of the like spectrum will actually be present at a like at a distance of 2 by t. So here actually 0 and 1 is what actually I'm seeing, sir. So it's what I like.
Do I
The
need to
unit
show again?
k is what is mentioned there, sir, as a unit on the right side, like on the x-axis.
0, 1, 2, 3, -1, -2, -3. There is spacing of 1 between the
Yes, sir.
coefficient.
Yes, sir. It's 2 pi, sir. Actually.
So then why taking that much time?
Okay. Sorry.
Okay, I have a sine wave. Okay,
Yes, sir.
like this one.
Okay, sir.
Is it visible to you?
Yes, sir. Yes, sir.
Peak value
Yes,
2
sir.
millivolt minus 2 millivolt.
Yes, sir.
I want to do half wave rectification.
Yes, sir.
How I can do? Just me design.
Okay, sir. Sir, I can put a simple diode and a load across. Like,
Do you think
it's
that
like.
diode will get on for millivolt range of the signal?
Sorry, sir. In this case, actually, I need to use an amplifier. Sorry. Operational amplifier based thing.
Have you listened the concept of super diode, some precision rectifier or not?
Yes, sir. I'm just going to draw that. Sir. Sorry. Just a minute, sir. So this will be the kind of block diagram, sir. Actually,
Okay, fine, no issue. Okay, fine, no issue.
Okay.
So, Pramod, see, you understand, I have assisted to you in every question.
Yes, sir.
Okay. But in many questions, you are doing a blunder mistake again. Avoid those. Don't be in the hurry. Okay. First of all, see the things what is provided to you carefully. Okay. So when I ask you, because you are dealing into power management unit, I have already told you study more about power dissipation. They can ask you what is the importance, why power dissipation is that much important factor. Okay. What are the other factors which get deteriorated because of this power dissipation?
Okay.
Is it clear? And band gap references circuit, just study about their history. They can ask, okay, what are their disadvantages? See, every technology is having some advantage and disadvantages. Okay, so they are applicable in high power application, low power application, where they are suitable. These sort of the question they can ask. Is it clear? Is it clear? What are the advantage of those, right?
Okay.
Getting clear? And what are the different sources of power dissipation in any of the integrated circuit? So it depends upon the what technology we are using. BJT technology, there are different sources of power dissipation. In Cmos technology, there are different sources of power dissipations. Usually we talk about the dynamic power dissipation, but there are many other power dissipation. Leakage current power dissipation is there. Short circuit power dissipation, which I discussed with you because of finite rise time and fall time, that is also there. So you must be knowing all the sources, okay? And they sometimes ask to derive these terms. Is it clear? Okay. And whether this power dissipation depend upon the dimension or not, so you explain in the elaborated way, the way you explain to me. Is it clear? Second thing is, in logic family, be very well about noise margin. okay, propagation delay time, and this fan out and loading effect. What are the disadvantage of if loading occur? So obviously what happened, the device is to operate properly as it is said to be overloaded. Working of the transistor will be affected, right? Propagation delay time will be affected, rise time and fall time will be affected. Is it clear? The transistor may damage, the speed will also get affected. Is it clear? Power dissipation, the each gate get affected. So there are so many effects. Is it clear? So go through these all facts, right?
Okay, sir. Any I had a question here. So any TTL logic families, any logic families they will ask. So I need to give away the answers in terms of propagation delay, rise time, fall time, power
you
dissipation.
need to give answer in terms of their specification and some more things they usually asking. Current hogging phenomena is there. You might have studied current hogging problem is there, right?
Sorry, I'm not aware of it, sir.
You can write this. There is a problem of current hogging.
Okay, sir.
And there is one current steering logic. Current steering logic.
Yes, sir.
Okay.
Okay.
And you can call it also as a current mode logic. So these are the two questions they recently have asked. Okay.
Okay, sir.
In reference to logic families. Fine.
Okay, sir. Okay, sir.
So rest thing they can also ask you to design some reference voltage circuit using Gina diode, using BJT. Okay. These basic they can ask you about IC regulator. What are the basic voltage IC regulators? Is it clear? They can ask their IC numbers, their power specifications. Is it clear? So these sort of the questions they can ask. Fine.
Okay, sir.
Sir,
so one thing actually probably like in my domain, sir, probably I don't feel that like I may be wrong, sir, but I just want to convey that maybe they can ask me how actually a low dropout design regulator might work, because we are not using those ICs, sir. Actually, the thing is that I am actually working on designing the ICs. Probably I don't know, like, because every industry has so many products on it.
What happened? There might be 4 to 5% in the panel, or might be 8 to 10%. Is it clear?
Yes,
so everyone is not expertise of this area in which you are working into. Is it clear?
Okay, sir.
Is it because when you say that the analog electronics is your favorite domain, then they can go into basic questions of this voltage reference circuit, right? Low power applications, high power applications. Then some of the faculty or professor or scientist can go into this domain. Is it clear?
Okay, sir, definitely.
Okay, so prepare on this line, right?
Okay, sir.
Rest, have you taken the introduction part with Vijendra sir or not?
Yes, sir. Yes, sir. I have taken. He said that no issues. Just convey him convey them the basic stuffs. No need to actually go into deep into like where all you have worked. So just say that you have 6 years of experience. If they go and ask you like where all you have worked in, so you can go and say them, like, then only it's like worthy.
Okay, no issue. You prepare on this line. Okay.
Okay, sir.
Okay,
okay. So my questions were just random questions to make you strong enough to respond there. If they ask some random associated question, right?
Okay, sir.
So one question I asked about Chandrayaan 3, right?
Yes, sir.
Chandrayaan 3 is just similar to Chandrayaan 2, but in Chandrayaan 3, we will not have orbiter. It will not have orbiter.
Oh, okay. Okay, sir.
Okay, in Chandrayaan 2, it was orbiter also present there, no?
Yes, sir. Yes, sir.
But this time orbiter will not be there.
Oh, okay, sir.
This is the basic difference. You can read about Chandrayaan 3 also, right?
Okay, sir.
Next coming project, because maybe you get opportunity to work in that project.
Okay, sir.
Then difference between conductance and conductivity. Sometimes they ask such questions which look very easy. We generally read these terms daily.
Yes, sir.
But whenever someone asks us to define, we are not able to define.
Yes, sir.
So conductance, conductivity. Conductance is the extrinsic property of a material, which depends upon its size, its shape. Accordingly, it may vary. But conductivity is the intrinsic property.
Yes, sir. Yes.
जो इनहेरेंट प्रॉपर्टी आ रही है ना इस किसी भी मटेरियल के अंदर, वो मटेरियल की प्रॉपर्टी है, दैट इज कंडक्टिविटी. So conductivity, resistivity, resistance, these terms you should know to define.
Yes, sir. Yes.
Rest all questions you answered correct, approximately all answers were correctly. And why do you want to join ISRO? These things you have discussed with sir.
Yes.
So I hope that you will answer good. Okay.
Yes, sir. Sir,
So
I was actually taking some short gaps when actually I was able to make out some statements. Is it okay to do that, or like?
no problem, no problem.
Yes, sir.
You should convey whatever is in your mind to them.
Okay, sir. Okay, sir.
If they get it, then it is okay.
Okay, sir.
Right?
Okay, sir.
Okay, all the best, Pramod.
Okay, sir.